Okay, this is lecture number 15 of this series. And as I have told you before, also that this is linked to the generator. And since generators are not very much in vogue, especially DC generators, so I have kept this topic as just as a small lecture, just like 20-30 minutes, not much from this one. Because nowadays AC generators are more in demand, and if you want to have a DC output, it's very easy to actually have a rectifier, and I guess rectifiers of almost every voltage and current rating are available. So it's very easy to actually just hook up a rectifier on an AC generator and you can get a DC. But still, since since shunt motors have been discussed, even the separately excited generators motors have been discussed, so why not a shunt generator and some conditions related to. So today's contents are related to the shunt generator, and then we are going to talk on the conditions of a generator also, which are marked over here. I will just talk on them a little later. Then how this shunt generator no load voltage is going to be talked about, and some linkage to the experiment which you have been doing in the lab, certainly the components of voltage drop, because there is certainly going to be a voltage drop, and the voltage drop is certainly going to be measured in terms of your voltage regulation. So for those of you who are not having an idea or they don't even remember it, then the voltage regulation formula was the V no load minus V full load, and then certainly this was being converted into some percentage scale. So this was your voltage regulation. And certainly for these two generators which I am discussing today, the separately excited and the shunt, they both have a positive voltage regulation, which means that as the load on them increases, the voltage drops. And what I mean by the voltage drop, I am actually referring to the terminal voltage VT that is actually having a drop over here. Now I have shown over here the two circuit diagrams, nothing special changing over here. The only thing different over here is this, that for a separately excited you actually require a DC supply. Now if you are in some isolated place and you don't have an access to some batteries or some other DC supply available to you, then certainly this generator is a no-go area. Then you cannot actually use this generator, and then it's better to actually use a shunt generator. But in shunt generator there are some conditions which have to be fulfilled, and those conditions I'm just going to discuss them. But before that, we all know whenever a shunt generator is being talked about and a shunt generator is being talked about, there is always a field winding, and that field winding is in parallel with the armature A1 A2. You can see over here the A1 A2 and F1 F2 over here. The load is also attached over there. The only difference between a shunt motor and a shunt generator is this, that if I make the current directions as a measure of differences, the field winding current direction remains the same, because if there was some supply supposedly over here, and if this was some motor, this direction would have reversed, this direction would have reversed, but this field winding current direction will remain the same. So the direction in the field winding remains the same, and certainly this field winding is going to produce that flux which is required by the conductor which is placed inside the magnetic field. This green color shaft and this arrowhead is actually depicting the prime mover over here, and that prime mover is actually going to give that mechanical energy, and that mechanical energy is going to be converted into some induced EMF, not back EMF. Back EMF is for the motor term. So this EA is actually going to be the induced EMF, and then certainly it has to pass through the armature resistance, and then that voltage which is available at this terminal is going to be called as VT, and this is also going to supply the field winding current. Now, in first place, we all know that a shunt generator is equal to, we know is a EMF is equal to VBL. Now, if you require E is equal to VBL, you have V over there and BL. V is being provided by the prime mover, and B is the magnetic field density. Now, if B is not present initially, if you are giving a mechanical energy to this one, your B is not being there because there is no field current initially, because field current is 0. So the EMF being produced by this generator, so if I write down this one, E is equal to VBL, the length is there, the velocity V is there because of the prime mover action, but V over there, that is the magnetic field density, is not there because the magnetic flux is not being produced. So the first condition of the shunt generator is this, that you should have a residual field inside your machine. Then what I mean by residual field, this means that F1 and F2, they are winded on some pole, and that pole has to be some ferromagnetic material so that it gives some flux, which means that this is going to give some residual flux, which means it will have some permanent magnetism. So that permanent magnetism is going to produce some residual flux, and it will be available for it over there. So initially, when A is going to be developed, this is going to be because of some residual B or residual flux over there, and then E is going to be generated. That E is going to provide that field current, and that field current is going to increase the total amount of flux over there, and the generator EMF will increase, and then again it will increase the field current, and this will continue to go on. So this means that the first condition of your generator, as depicted over here for shunt generator, is residual field. Now this condition of residual field is not required for a separately excited generator, for obvious reason, because for field winding F1, F2, you have a separate supply. But again, this supply, if it is not available, then certainly you need to hook up a shunt generator over here. The second condition, as you can see, is this written over here, is the assistance to the residual field. Now it may be possible that there was some residual field over here, and it gave some residual flux to the EA that was being produced over there. So what I mean by this, that there was some EA produced over there, and certainly that was because of the residual flux. Now what happened over there, that this produced some voltage at these two terminals, so that the current actually started to flow. But this current flow, which was flowing over here inside the field winding, it was, instead of increasing or adding its flux with the residual one, it was actually decreasing it. So what I mean by this over here is that if your total flux over here is equal to phi residual minus your produced flux over here, so what is going to happen, your total flux, net flux, is going to actually reduce. So practically, if the winding current is not going to aid the residual flux, which means that on your pole, so if I have some poles over there, and that pole is going to produce north pole over here, south pole over here, but if the current is flowing over here in this direction, and it produces a south here and north here, so effectively, instead of actually having addition in the flux over there, you are actually reducing it. So what will happen, that your machine is not going to actually get a kickstart. And I guess you have been experiencing this problem in your lab, and you have been doing this one very carefully. And what you have done, you have been actually changing the terminals of your field winding. So you have been doing it very clearly over here. You just swapped the two terminals over there. Either you swapped A1, A2, or either you swapped F1, F2. And what you do by this, you are actually changing the assistance to the residual field. So this is very important, that these two conditions for shunt generator are always met whenever a shunt generator is actually being run. So a third condition is also there, but I will comment at the end of the lecture, because that's very, very important from that point of view. Now coming on to your shunt generator, I guess you have done this previously in your lab also. The KVL equation is there, just writing just like the outer KVL equation for the outer loop over there. You can write it over here as minus VT, because we're starting from here. So this is minus VT, and then there is minus IARA, because current IA is flowing out of it over there. And then I have plus EA, because this is the source which is actually going to provide all the energy. So VT is equal to EA minus IRA, and this is completely opposite to what it was in motor. In motor, it was EA plus IARA. So now this is actually easily telling you that the output voltage you are going to get is approximately equal to EA, whatever voltage is induced inside, minus IARA. And there are three voltage drops which are evident over here. One is the drop over here because of the resistance of the armature winding, which is shown over here, and you can see this is linearly increasing over there. So as the current IA is increasing over here, on the x-axis I have my current IL, where current IL is actually equal to IA plus IF, because this is a shunt generator over there. The next thing is the armature reaction drop over there, and certainly if you don't have any compensating windings inside your machine, then certainly your net flux is actually going to decrease. And when your net flux is going to decrease, your flux is actually also going to decrease over there. And you can see that if you include armature reaction, then this white color waveform is actually, so you can see when IL is increasing, the armature reaction drop over here is increasing as the load is increasing. And then the last one is the field current decrease over there, that is IF decrease over here. And what is IF decrease over there? Because when you are increasing the load over there, the terminal voltage at these 2 points, which is actually VT over there, is decreasing down because of the larger drop across IARA. So what happens? The field current decreases. The field current is not a constant value no more. So what happens that as the load current is increasing, your VT is decreasing, and when VT is decreasing, it is decreasing field current more, and when EF current is being decreased more, this means that less EA, and less EA means then again less EIF. So it's actually going to be the most dominant drop inside your shunt generator. In separately excited generator, if we move on, this is going to be supplied from a separate supply, so this last IF decrease is not going to be there. But if all of these three drops are not there, which is practically not possible, then you are going to get a straight line as over here. Thus EA is equal to VT, and over here at this point you can see this is EA at IL equal to 0, which means that the load is not there. Now if you want to have the EMF being measured over here, so you are going to go towards your magnetization curve, and I have now made this machine at no load. Now you can see over there, this is at no load, which means I have just hooked up a voltmeter over there. Now in this voltmeter over there, you can see I have added some shunt resistance over there. This is the resistance of the field winding, and it's the same experiment which we have done previously, but this time I'm not talking about in terms of the field current increase and whatever happening. I'm going to tell you that how the generator actually increases. So supposingly you have made your shunt resistance fixed at some point, supposingly. So on this curve over here, I have EA and I have IF over there. So we know the magnetization curve. This is the magnetization curve, and supposingly you have plotted it before. Now based on whatever field resistance you have selected over there, that is actually R small f over here. So this RF will be having a voltage corresponding to EA, because when this will be at no load, we can say that VT is approximately equal to EA. So this means that the field current over here in this case is going to be equal to, so my IF is going to be equal to EA divided by my RF over here. So now what this means over here, that this is going to be a slope line over there, and this slope line, this RF slope, certainly if RF is large, this will be having a more slope, but if RF is small, so what this means by that, this white line is actually going to, supposingly if this white line was not like this and it was something, let me use some other color, and it was supposingly going to cross it in a straight line over here, supposingly. So the point at which it's going to cross it, supposingly at this point, that is actually going to be the point that generator is actually going to work at. So this is going to be the point at which the VT at no load, or actually because it is working already at no load, so VT will be equal to EA is going to be the official voltage. So at no load, but over here, this is going to be the point when you have fixed it at RF, and certainly this value is, supposedly if I call this one as RF1, this one as RF2, as the slopes are actually telling you that RF2 is a more steep slope. So certainly resistance RF2 is certainly larger than your RF1, which means that that's current in RF2 case and higher current in RF1, which certainly means more flux. More flux means that you are going to get more EMF. So you have just found out that you have this point as the maximum point. But how this point is going to be reached, just like that, if you see over here in this whole shaded, not a shaded region actually, the two intersection of the two curves over there, if you see very closely, your magnetization curve starts not from 0 but from some value. Now this value at which this is going to have the magnetization curve, this is actually called as the EMF because of the residual flux. So you can see this is starting from not a 0 value. So even if your field current is 0, you are going to get this residual flux. And now if your residual flux is being aided by the field current, so what will happen? You are going to actually have the IF increase, and you can see this arrowhead over here, the laser marker over here, and then because of this field current increase, you will have an increase in your EMF, and it will reach this point of the magnetization curve. And then because of that EA, you will have another increase in the field current, and then you will have another increase in your EA, because this yellow color line is the EA and the white color line is the actually the slope of the field resistance over there. So again, this will continue this staircase increase, and a point will come when this will go up till the maximum over here. So if I can just show it over there, so when this will move up over there and this will reach up till this point. So many of you must have witnessed this one in your lab also, that when you have actually made the swapping of F1, F2 or even A2 and the residual flux was being aided by the field current. So the staircase of the increase in the field current, or actually the EMF, is visible over there, and this takes place in just like maybe like some seconds or some milliseconds. Even if the machine is going to have a big mass or inertia, then certainly it will be a little smaller because of the resistance and the mass over there. But technically, this increase of staircase between the EA, that is actually the magnetization curve, and the RF slope is actually the starting of your generator from basically zero. But again, they based on the two conditions, that it should have a residual flux and it should have the residual flux being aided by the field current. So the staircase approach, that is actually the increase of the EA from certainly the residual flux EMF over there. Now when you are going to attach a load on this generator, now what will happen? Again, this curve is going to be beneficial over there. Supposing you have reached this point over there and your load is now attached over there. Now this load attached over there is going to give you, this point over here is giving you that VT at no load over there. Now, you know, when the machine is going to work at load, there is certainly going to be some drop over there because of our IARA, and the field current is also going to drop. Then certainly the generator is not going to work at this point. So the next thing, I am assuming in this diagram at present that armature reaction is not present, or in fact I am not taking that into consideration. In the next slide I am going to take that into consideration. So what I have done over there, since IARA, which is actually going to be the main drop over here in which I am considering in this slide, is actually a voltage, because V is equal to IR according to Ohm's law. So IARA is actually a voltage value. So that's why on the y-axis I have my voltage over here. So what I have done over there, I have made this vertical lines over there. These vertical lines are parallel to my y-axis, and these y-axis points are made parallel in such a way that they are corresponding to some value of IARA. So what happens over there, if you know your current IA, you can calculate your IA multiplied by RA, and according to your graphical scale, whatever you have been using it over there, wherever it fits in. So if your IARA, according to your graphical scale, it fits in over here, this is going to tell you that what is your practical EA at load and what is your VT at load. Now, if load was not there, then this was your EA or VT at no load. But when the load is attached, your field current is also going to drop. Why? Because the voltage EA, when passing through the resistance, reaching this point, that is actually VT over there, there is going to be a drop. So certainly there is going to be some voltage drop over there. That voltage drop, accounting it, you have your EA and VT over there, and these are at load. So your IARA is going to be converted according to a graphical scale on this chart, and wherever it fits it. And certainly, since this is going to be a curve something like this in a parabolic shape, so maybe this length equals here also and this length equals here. And certainly you are going to take the higher value, because certainly the generator is going to first of all follow this path over there. So at this point, supposedly if your IARA drop is small, then this is this point. So corresponding to this one and corresponding to this one, these are going to be your EA and VT at load. So if your load current changes and certainly your IA current changes, so this point over here, that is the vertical lines over there, which are each vertical line represents the IARA drop. So what you are seeing over doing in the last slide, what we had over here, we had this magnetization curve, and using the magnetization curve and the RF slope, we just found out that how the generator actually started from the residual voltage up till the no load point. And now using the very same curve, what we have done, we have got the no load voltage also, but now we have got attached a load, and certainly there's a variable load shown by this arrowhead over there. So if you know your IA, based on that IA, you can convert it IARA into some vertical length over there, and you can find out your EA and VT. Now, one thing which we have just not included in this chart is actually the armature reaction. Now, if you want to include that chart over there, that chart can be included in this way over there. How you can see over there, instead of now adding one vertical line over there, now what we have done over there, if you see very closely, I have added one triangle over here, and this triangle has two vertices or two sides over there. One is the IARA, just like the very same, and since on the x-axis I have my field current. And what does armature reaction do? It actually decreases the net amount of MMF available. So this is actually a demagnetizing MMF. So what it does is actually reduces the amount of IF, or the available IF, or the useful IF over there. So if you have your value of armature reaction and you have converted it into the MMF for the armature reaction reduction, so that MMF over there, convert it into your field winding over there, dividing it by, so if you remember it from your motor configuration, this was your armature reaction MMF, and dividing it by NF, that was the actual net decrease in the IF over there. So this decrease over there depicted over here by this x-axis and this y-axis. So this triangle, wherever it fits in, that point again is going to tell you where is the EA and where is again VT. Now, if that triangle is smaller, supposingly, maybe if your triangle is somewhat here, let me make this over here. So if this triangle is somewhat here, so this is your IARA, this is your IF decrease over there. So corresponding to this point and corresponding to this point, you are going to get the EA and VT. So if I can make it again, sorry. So this is my EA and this is again my VT over there. So larger the triangle, certainly you will have to come down over there, and then corresponding to this one, you are going to get your EA and VT. So now, having this IARA and the demagnetizing MMF, or the corresponding armature reaction MMF divided by NF, that is actually the number of turns on your field winding, over here, you can actually find out with all the three drops, just from the magnetization curve and the RF slope over here, you can find out over there. But yes, certainly you need to find out first of all the RF slope. Now, if your RF slope is different over here, then certainly you are going to have a different value of what I mean by this over there. So if supposingly your RF slope is different over there, supposingly if RF slope is here, so corresponding to this point, this is going to be your EA at no load. So certainly this area actually comes down. So what happens over there, when you are actually going to have a larger RF, your possibilities are going to be very small, and in that case your generator is not going to be very stable. So if you want a generator to be on the very stable side, it's much easier to actually make it in such a way that it is going to be stable. For this purpose, what I have done over here in this next slide, I have a critical field resistance term, and what this term actually does over here, I have again a magnetization curve, but here I have plotted 4 different field winding resistances, which means that by adding a shunt resistance over there, I am changing the field winding current over there. So what I have over here, I have RF4, I have RF3, RF2, RF1, and all of these are linked by these values over here, or this inequalities over there. RF1 is certainly larger. Why? Because you can see this is having the most steepest one, the next one is RF2, the next one is RF3, and the next one is RF4. So you can see RF4 actually intersect at some point, and that gives me that value of no load over there. If RF3 is there, certainly this region in between the two curves is very small as compared to certainly RF4. And if you see RF2 is like something very, very strange over there, because this is intersecting here, it's also intersecting here, it's also intersecting here over at this point. So you can say that RF2 resistance, if it is set for the field winding, it is going to be an unstable condition, because maybe the generator is working at this point and there is a slight disturbance in the load or on the prime mover speed over there. What will happen? The generator will fall down quickly to some value. But if you keep it at RF1, you can see it's not even crossing. So it's just crossing at this point. So the voltage is almost equal to the residual voltage over there that is inside. So you are actually not giving enough field current to your field winding so that it can actually produce it. So RF1 is the higher resistance than all of these four over there. So this means that RF1 is the higher value and RF4 is the smaller value. And if you have to pick off all these four, RF2 is the critical field resistance. This is that field resistance at which the generator is not going to generate any voltage, or you can name it as that value of field resistance which is required, or at least the resistance has to be smaller than this critical field resistance for the generator to actually produce some voltage over there. So RF2, where it actually coincides with the magnetization curve, the yellow color curve over there, and it is practically unstable generator position, so that's why it's going to be called as critical field resistance. So whenever you want to run a shunt generator, you have to keep your field resistance smaller than the critical field resistance over there. So I guess many of you have plotted this magnetization curve in your laboratory. So if anyone asks you to actually find out the critical field resistance of your generator, I guess you can very easily do it. You can just find out the slope of this region, that is a linear region of your magnetization curve, and you can do it very easily, because if you just need to find out, you just need to take the y value and x value. So this is y, this is x, and dividing y by x, this will give you the resistance of your field circuit, and that will be something like 800 or 900 ohm if I'm not wrong. So this will be the critical field resistance. So your resistance of your field winding should be somewhat less than this value. So critical field resistance is that third condition which I just told you in the very start, that your condition for the third condition for a shunt generator is the critical field resistance value. So the value of the resistance of the field winding has to be less than, so your field winding resistance has to be less than the critical field winding resistance over here, so that the shunt generator can actually produce the voltage available to you. So this was all for today, and this is lecture number 15. But again, as I have given you a remark in the very start, that DC generators are now obsolete and DC generators are obsolete because AC generators can be easily be giving us a DC voltage out, when you can attach just a rectifier of any other voltage and it can work on very easily. So DC generators are little obsolete, but yes, they are still available. Maybe in some places, if you have happen to a chance to go to Mangla Dam or Tarbela Dam, because they are little old erections in 1960s or 70s. So at that time, whenever there was DC supply required for those dams, and we will talk about that when we discuss AC generators at that time. I will tell you that why those DC generators are still installed over there. They are not working now, but they are still installed there, but because of the erection there, they are still standing there, but practically their usability is zero at present, but because of the structure and all that stuff, it's erected over there. So this is all for shunt generator and separately excited generator. So thank you.